So this is another video for practicing problems for our exam. Again, I hope this helps. And let's just get into it. I want you to draw the Lewis structure for CH3CN. Alright, well, I have a CH3 right there, so I instinctively know that my carbon is going to have 3 hydrogens bonded to it, and it's going to be directly connected to this carbon. Right, I'm just reading left to right, okay? It's like a sentence. And then that carbon is going to be connected to a nitrogen. So we're done, but notice that this carbon is kind of having some difficulties, right? We want to have 4 bonds, but notice that this carbon right here already has 4 bonds. So the only logical thing that I can do to get 4 bonds for the central carbon is to have 3 other bonds towards nitrogen. Alright? And, well, I kind of want to show you how to do formal charge as well. So what's the formal charge for nitrogen? Well, we usually count how many electrons we have. So every bond is worth 2 electrons. So we're going to say 2, 4, 6, and 8. 7 and 8. Alright? Nitrogen usually has 5 electrons. So nitrogen, carbon, so you have carbon, nitrogen, oxygen, and fluorine. They're going to have 4, 5, 6, and 7 electrons. Alright? So since nitrogen has 5 electrons in its wallet, we're going to subtract 2 electrons. That's 1 and 2. So 5 electrons minus 2 electrons will give us 3 electrons. And now we're going to subtract the bonds. So we would have 1 bond, 2 bonds, and 3 bonds. So 3 electrons minus 3 bonds would be 0. 3 minus 3 is 0. So our formal charge is 0. Alright, that's pretty cool. Let's also go over just for reasons, right? Let's go over primary, secondary carbons as well. Alright. Alright. So what is this, a primary, secondary, or tertiary carbon? Well, it turns out that this is a primary carbon. You may be wondering, how is it primary? It's connected to 2 things. Well, primary carbons only care about being connected to other carbons, right? So this carbon is directly connected to another carbon, right? So that makes it a primary carbon. And the same is true for this one. We are connected to 1 carbon. It doesn't matter that we have hydrogens connected to us. They're not carbons. So we're going to just be focusing on carbons to carbons when we're naming our primary, secondary, or tertiary. Right? Whenever you're doing these types of problems, you just kind of want to read from left to right like a book. In this case, we have an OH, which turns out to be an alcohol. So let's write that down. We have an H connected to an O. That oxygen is connected to a carbon. That carbon has 2 hydrogens. And whenever you have 2 hydrogens, it's just safe to assume that the hydrogens are going to be branching outwards, not inwards, so we don't do this, right? Don't do that. You want to branch it up and down. So CH2, that carbon's connected to another carbon that has a hydrogen. And, yeah. And it's an oxygen right there. Alright? Yeah, so everything's pretty good. If you got stuck and you probably just do oxygen, like here's what I recommend. I recommend that you read the sentence from left to right and just draw down the basically like the fundamentals, like the bones. This is the bone, right? And then we look, it's like the most basic structure. And then we're going to look through our molecule to see if there's any proper bonds that we need to add, or any formal charges or something. So in this case, oxygen is pretty good. Oxygen loves having 2 bonds, right? So we're going to count the formal charge. A formal charge of 0 is like the best. You always want a formal charge of 0. So 2, 4, 6, and 8. Oxygen has 6 electrons that it normally has. So 6 minus the 4 lone electrons. 6 minus 4 is 2. And then 2 minus the 2 bonds, that is 0. So we have a formal charge of 0 for oxygen, and that's good. So we leave it alone. Carbon has 4 bonds right here, and that's always good. So we leave that alone too. But notice that this carbon right here has 3 bonds, and we can't make a bond right here. Like that's not a good move to do, right? Because then this carbon would have 5 bonds, and that's not good. So the only logical thing that I can add is a bond right here for oxygen, because hydrogen can only do 1 bond. Oxygen can do 2, like more than 2, but we're happy to do 2, right? And we're going to count the formal charge for this. So 2, 4, 6, and 8. And it's the same thing. 6 minus 4 is 2, and 2 minus 2 bonds is 0. So our formal charge in this whole molecule would be 0. So again, I just recommend that you read the molecule structure, the condensed structure from left to right, fill in the bones, and then from the bones, you add more bonds, and you calculate formal charge to see if it's actually correct. And take your time on these, because some of them can be pretty tricky. For this problem, I want you to draw out the Lewis structure, and then from the Lewis structure, I want you to do the line formula. So let's begin. We have a CH3 right here and a CH3 right here. These are called terminal points, right? And these terminal points are pretty easy to map out. We're just gonna have these terminal points in a nice turquoise color, my favorite color, right here. Okay, CH3, CH3, CH3. Now going from left to right, we are attached to a carbon. That carbon has 2 oxygens attached to it. And you could do an oxygen right here and right here. I did this because if I just had a oxygen right here and an oxygen right here, we would have 3 bonds. So instinctively you would say, well, it's either here or here, but I like putting my double bond on 1 oxygen, right? Whichever is your preference, really. Carbon. Well, actually, if you were to do the bond right here, you would have a triple bond for oxygen, so that's not good. You know, you always want to have oxygen with 2 bonds and not 3 bonds, right? So we're attached to a carbon. That carbon has a hydrogen. 2 hydrogens, actually. And we have a nitrogen. That nitrogen will be attached to a hydrogen and have a carbon. Well, let's make that in a nice turquoise color to illustrate that this is a terminal carbon, right? Okay, cool. Do we need to add any more bonds? No, if I add bonds right here, carbon would have 5 bonds. Same thing for this carbon, not good. This has 2 bonds, good. 2 bonds for oxygen, that's good too. So all that we need to do now is add formal charges. Everything seems pretty neutral except this nitrogen, so let's count how many lone pairs and what's its formal charge, right? So 2, 4, 6, 8. Right? Nitrogen has 5 electrons that it has normally in its wallet. So 5 minus 2 electrons is 3 electrons, and 3 electrons minus 3 bonds turns out to be neutral. So overall, this whole molecule is neutral. All right. So let's draw out the line formula, right? So the line formula has carbon, 2 carbons, an oxygen, a carbon, a nitrogen, and a carbon. And if you want to be a little bit more precise, this is a hydrogen that's connected to that carbon. This is a hydrogen as well. So let's write out our are add-ons, right? So that's a carbon, this is a carbon, but that second carbon is double bonded to an oxygen. Okay. That nitrogen has this as well. Alright. Now we're going to be adding hashes and wedges. Now here's an important thing for you to know, especially if you're going to be taking the MCAT or any type of ACS national exam. We're going to have to count electrons right here, right? So 2, 4, 6, and 8. Right. We have 4 houses. This is an electron group, or you could say house. This is also a house. That's a house, and that's a house. So oxygen's neighborhood consists of 4 houses, right? There are 4 electron groups. Bonds, no matter if they're double bonds, triple bonds, or single bonds, if they're just connected between 2 atoms, like that's a house, that's still one house, and that is also one house, right? Now, I know this isn't possible, okay? This isn't possible to do because oxygen would probably be messed up, but that would have 2 houses connected to oxygen. That counts as a house, and that's a house as well, right? So the main thing I'm trying to tell you is that whenever an atom has 4 houses around it, you're going to have to put the lone pairs or whatever is surrounding it that's not a bond in the hash and wedge. So in this case, oxygen has 2 lone pairs surrounding it. So on my wedge, I'm going to have some electrons. And then in my hash, I'm going to have some electrons again because they were surrounding me in oxygen, right? In this case, for oxygen with the carbonyl, with the double bond to carbon, well, let's see how many houses we have. 2, 4, 6, and 8. 8. So that counts as 1 house, 2 houses, and 3 houses. And there's 3 houses, not 4. So that's not good. It's only for 4 houses, not 3. And therefore, we're not going to have anything on our hashes or wedges. It's just going to be invisible. Kind of like how you imply that hydrogen is connected to a carbon, right? We're not showing a hydrogen bond right there. We're just implying it. We have to assume that it's there. We're going to assume that our electron is on this oxygen right there because we are not connected to 4 electron groups. Okay. Well, what about nitrogen? Okay. Well, nitrogen right here has 1 house, 2 houses, 3 houses, and 4 houses, right? Hydrogen counts as a house, as an electron group or whatever is surrounding us. So that must mean that we have a wedge going like that. It doesn't matter if there's an electron right here or a hydrogen. You just got to put something in the wedge or hash. It's one or the other. It doesn't matter, okay? For viewing purposes, we're just going to put some electrons right there. And then my hashes go backwards, and that's an H. You don't have to fill in your hashes like this. It wastes time. And you don't need more than 3 wedges to show that something's going backwards into the page. It wastes time, okay? And now we're just going to be filling in our hashes and wedges right here. So carbon is with hydrogen. That's another hydrogen. Whenever we have our peak going upwards like a mountain, we have to continue going upwards like a mountain. So we go backwards, H, and like that, H, H. This is a pretty fun problem, right? Lots of pretty colors. For this problem, I want you to find the hybridizations, the electron pair geometry, and the bond angles of the selected atoms in this molecule. So for question 1, it's asking us for the first oxygen, which is oxygen number 1. And what I like to do for these types of problems is I like to break my molecules into fragments, right? So we're just going to be focusing on this section right here for this part. Okay? Well, we have an H attached to an oxygen. That oxygen is attached to a carbon. All right? I need to find the hybridization. So 2, 4, 6, and 8. And 6 minus 4 is 2, and 2 minus 2 is 0. So our forward charge is neutral, and we gotta check our houses, right? We have to check our houses. We have 1 house, 2 houses, 2 houses, 3 houses, and 4 houses all together. And the way we find hybridization is that we add up our houses. So we have S1, P, doesn't look like a 1, S1, P, and 3. Why do we have SP3? Because 1 plus 3 is 4. We have 4 houses, so we need 4 orbitals, right? And we're just going to write it right here. This is SP3. The 1 is invisible, right? And the electron pair geometry would be tetrahedral, because 4 is tetra, so tetrahedral. And for tetrahedrals, you're expecting a 109 degrees for your bond angles. Okay. Now, for carbon 2, we're focusing on this carbon right here. So that carbon is basically right here, oxygen connected to a carbon. Well, we're just going to be focusing on this guy. But we have 2, 4, and we're implying hydrogen, so we're just going to assume that we have hydrogens right here, right? And as it turns out, that hydrogens classify as what? They classify as houses. So 1 house, 2 houses, 3 houses, 4 houses is the same as the other molecule. So it's going to be sp3 tetrahedral. And tetrahedrals have a 109 degrees bond angle. Now we're going to be focusing on this carbon. And we're going to be focusing on that carbon, so let's do that. We have a carbon double attached to a oxygen. And that carbon is attached to 2 other carbons. So what is our hybridization? Well, we have 1 house, 2 houses, and 3 houses. How many bonds do we have? Well, if you count the bonds, we have 1, 2, 3, and 4. 4 bonds, carbon is neutral, carbon is good. But notice that we only have 3 houses. So what is this? S1, P2, because 1 plus 2 is 3, right? That's what you want. So it's a sp2. And you know what is cool about this? That the 1 and the 2 give you a degree, 120 degrees. So sp2, this is called trigonoplanar, trigonoplanar, because tri is 3, trigonoplanar, and like we said, that's 120 degrees. Pretty cool. Now this one may seem pretty tricky, but we're going to be doing C5, which is this right here. We're going to be focusing on that. Well, let's do it. We have a carbon attached to a carbon that is attached to another carbon, but this one is actually positive carbon. So how do we explain that? All right? How do we explain that? Well, normally when you have a carbon attached to 2 other carbons, you're going to assume that it has a hydrogen. But whenever you have a partial positive carbon, it actually means that you have 1 hydrogen. Why? Why is that? Well, you want a partial positive, right? So let's count the electrons. That's 2, 4, 6, 7, and 8. All right? Carbon has 4 electrons in its wallet, and 4 minus 2 is 2. Let's see. Yeah, it should be, right? Because you have 2, 4, 6, 7, 8. 4 minus 2 is 2, and 3 minus 3. That's a weird one. Yeah. Well, let's figure this out. Because this, like I said, is pretty tricky to do. How do we do this? 2, 4, 6. Well, if it's positive, then it wouldn't have those electrons, right? Because let's assume that these electrons were bonded somewhere else and we lost them, and now they're empty, and so we're pretty hungry. We're going to be acting as what? An electrophile, which wants electrons. We're pretty hungry for electrons because we have this void in our stomachs for more electrons. So instead of doing the mistake like I just made, right? Because that's going to happen on the exam, so don't make that mistake. When you have a partial positive carbon, you don't have any electrons around you. So let's do 2, 4, 6. There's no 8 electrons, there's only 6. We have a gap, and that means we want electrons. And 4 minus 3 is a partial positive. Okay? So 4 electrons minus 3 bonds would give you +1. Alright? That was a really good example. It trips a lot of people up. So that's 1 house, 2 houses, and 3 houses. So since we are 3 houses, we are at S1, P2. 1 plus 2 is 3. So that becomes a what? It becomes a sp2. An sp2. Trigonal planar with a angle of 120 degrees. All right. Now what about N7? N7. Whenever you're doing these types of problems, just write out your electrons, right? So write out your electrons. 2, 4, 6, 7, and 8. Now let's count the nitrogens right here. Nitrogen has 5 electrons, so 5 minus 2 is 3, and 3 minus 3 is 0. So our nitrogen is neutral. So let's count the houses now. We have 1 house, 2 house, 3 houses, 4 houses. Since we have 4 houses, we have 4 orbitals. So that is a S1, P3. 1 plus 3 is 4, right? So that's a tetrahedral. 109 degrees. Okay. And then the O9 right here, focusing on this boy. So 2, 4, 6, and 8. Always draw your electrons. Now, how many houses do you have? 1, 2, and 3. 3 houses. Since that is 3 houses right there, that's S, 1, P, and 2. 1 plus 2 is 3, and 3 is tri, and then gonal planar. 120. Pretty tough question, but I think it's really worth it. It's, kept me on my toes. It's pretty good. For this problem, I want you to find the formal charges of each molecule, or of each atom, right? And for funsies, we're also gonna do a functional group review, right? So I'm assuming that you've taken a crack at it. Let's do it. What I like to do is draw out my electrons. So 2, 4, 6, and 8, right? 6 minus 4 is 2, and 2 minus 2 bonds is 0, so that is neutral, check mark. Let's do 2, 4, 6, and 8. 6 minus 6 is 0, minus 1 is a negative charge. That is a negative charge right there, negative charge. What about the nitrogen? Well, this nitrogen is connected to 2 carbons, right? Is connected to 2 carbons. Let's see, 2, 4, 6, 8. Our electrons are full, so we don't have any electrons to subtract 5 from, because nitrogen instinctively has 5 electrons in its wallet. So 5 minus 0 is 5. 5 minus 4 bonds is a partial positive. It's a positive charge right there. So we have a positive charge. Okay. Now we're going to do our functional groups. What is this? Well, notice that this nitrogen is connected to a carbon, and that carbon does not have any oxygens to it, right? So since we're connected to a carbon that has no oxygen, we're just surrounded by carbons, we're going to be mean people. We're going to be some bullies. We're going to, corrupt the world and change society. We are a mean group of people. We are amines, right? Or amines. But I call them amines for that mnemonic. So this right here would actually be called an amine. But to be more specific, is this a primary, secondary, or tertiary amine? Well, how many carbons are we directly attached to? Turns out we have 1 carbon and 2 carbons. Okay. Well, that must mean that we have a secondary amine. So this amine is a secondary amine. Amines and amides, when you classify them by their direct connection to carbons. So we're not going to have some nitrogen attached to a carbon that's attached to 2 other carbons and say, hey, this carbon is attached to 2 others. That must mean that we have a secondary amine or amine. No, it's only considering the direct connection, right? And can stand for next to, right? We're next to, 1 carbon, right? So that must mean we have a primary, let's just say NH2, primary amine. All right. Now what about this carbon, since we're talking about carbons? Well, that carbon is attached to 1 and 2. Okay. And that carbon right here, right there. All right. So that must mean that this carbon is 1 group and 2 groups. So that is a secondary carbon. And what about this? So this carbon is attached to only 1 other carbon. So right here, this would be a primary carbon. Right, because we're only attached to 1 other carbon. And what is our functional group right here? What is our functional group? Yeah, that's actually an ester. That's an ester because, well, if you ever celebrated Easter, right? Easter, you go to backyards and you collect Easter eggs. Well, an Easter egg kind of looks like this, right? It's like an oval or something. That's a pretty bad representation. That one too. But what I'm trying to say is that an oxygen kind of looks like an egg. And whenever you find an Easter egg, there's usually other Easter eggs near it, right? You're not going to find an Easter egg and then 5 miles down the road, you're going to find the next one. No, they're in like the proximity. They're like right next to each other. And so an ester has 2 oxygen, 2 Easter eggs that are connected. And this little carbonyl could be your little sidewalk that you go to get your Easter eggs, right? It's like a sidewalk that you go on. So this would be called an ester. And just for relevant purposes, what is our carbon? Is it a primary, secondary, or tertiary? Well, that carbon is attached to another carbon, right? So we're not going to consider these oxygens. Just ignore them. We are only considering this carbon-carbon bond. We are only attached to 1 carbon. So that must mean that this and this one right here are just for relevant purposes, this 1 carbon right here is a primary carbon. So that's how you would do those types of problems. And just remember, for nitrogens or amines or amides, you count how many carbons are directly attached to it. In this case, we have 2 carbons attached to us. That makes us a secondary amine. And for carbons, you're gonna consider how many carbons are attached to it. So we have 1 carbon attached to us and another carbon attached to us. That makes that one a secondary carbon. All right. It's pretty hard to understand, but if you do it a lot, I promise that you'll understand it. So this is an arrow pushing problem that is complicated, right? As you can see, we have step 1 and step 2, right? Well, what may seem a little daunting to you, a little bit confusing, is how it's structured. So we got to show how our products came from our reactants, right? So what can we do to these reactants to get this? And then what can we do from this to get this? Alright, so that's all we're doing, that's all we're explaining with arrows. What I like to do with these types of problems is to just write out the electrons, because the electrons are going to be our blood when we're doing these problems. So starting with oxygen, we have 2, 4, 6, and 8. Okay? Then 2, 4, 6, and 8. Okay? And notice that this oxygen right here is a negative. So to get oxygen to be a negative, we already have a hydrogen bond, right? We have a hydrogen bond, so that's 2, 4, 6, and 8. 6 minus 6 is 0, minus 1 is a negative 1. So that must mean that this oxygen has 3 lone pairs. All right. 6 minus 6 electrons is 0. 0 minus 1 bond is negative 1. Right. Now for this oxygen, we have 2, 4, 6, and 8. It's the same thing. 6 minus 6 is 0, minus 1 is negative 1. And what about our bromine? Well, our bromine turns out to be, our bromine becomes 2, 4, 6, and 8. So it stayed the same. And what about this one? What about that one? Well, it turns out that this oxygen is going to be double bonded, right? So that's 1 bond, 2 bonds. So 2, 4, 6, and 8. 6 minus 4 is 2, and 2 minus 2 is neutral, right? We will have 2, 4, 6, 2, 4, 6, and 8. That is neutral as well. This is neutral too. Just showing you for experience. And this bromine is going to have its full valence shell. It's going to have a bunch of electrons. So 2, 4, 6, and 8. That's what it means to be negative. Right, so how do we explain this? Okay, well, a proper arrow pushing mechanism needs to explain how you got bonds made, how bonds were destroyed, how things became negative, and how things became positive. So we're going to look at our structure for right here and focus on this part. We're not going to focus on this, okay? That's on a different step. We're not related to it, okay? So what changed? Well, I noticed that one of my double bonds changed, right? That changed. And I noticed that this alcohol, or this OH, right, bonded to my carbon right here. Okay. And we need to explain how it did it. Right? Well, am I gonna draw my arrow right here? No, I'm not gonna do that, because carbon doesn't have any electrons to give. It's pretty poor. Like, it doesn't have any money to donate to charity, so it's just gonna, not have any money. However, we can take some electrons, some money from our OH, and transfer it to carbon. But wait a minute. That gives carbon a 5 bonds right there, and that's pretty bad. 1, 2, 3, 4, 5. So whenever you have 5 carbons, it can't handle the stress. It's like taking 30 hours at college, and it just breaks down. So this double bond from oxygen transfers its electrons to the oxygen. So it's going to transfer some of the electrons right there. And that explains these electrons, okay? All right, nothing happened to this bromine, so we're going to leave it alone, right? So that basically explains how to do the first part. Now in the second part, which we're going to do in nice turquoise, we are trying to explain how this bond came to oxygen and how bromine separated, right? So how do we explain that? Well, we're not going to really worry about the OH group right there because nothing happened to it. Whenever something stays the same, we ignore it, okay? In this case, we're going to try to figure out how to make oxygen more positive. So this oxygen is neutral, right? We're going to call it neutral. And neutral is more positive than negative. And whenever something's negative and it wants to be more positive, it vents, right? You vent to a therapist and you lose your negativity, all right? So that must mean that we lost some electrons to become more positive. So oxygen saw a therapist and became more positive, all right? So am I gonna take some electrons and put it right there? No, I'm not gonna do that, because if we did that, we're gonna have like a double bond to bromine, right? And that's not good. That doesn't explain how we end up right here, right? So we're not going to do that, at least not yet. Instead, we're going to take some electrons and put it right here. That pair of electrons shows up right here, and then it gives us a carbon that's hungry. So this lone pair right here attacks the hydrogen, or attacks the carbon, and the carbon becomes neutral again, right? So now our electrons are going to move to this carbon, and it's going to make a bridge, which you see right here, to the oxygen. So again, whenever you're doing these types of arrow pushing problems, just write out your electrons first, and then realize that you cannot draw arrows going from carbon to another molecule, because carbon typically doesn't have electrons to give out, right? Whenever something doesn't change, ignore it. Whenever something changes positive to negative signs or anything like that, you gotta pay attention to it. And don't feel overwhelmed over how many steps there were, all right? Because again, you're only focusing on this part right here, and then kind of like this overlap right there. So this is going to be, step 1, and this is going to be step 2. All right, just break that into its parts. So this middle one shows up for step 1 and step 2. I want you to rank these molecules from 1 to 3, 3 being the lowest and 1 being the highest, on its boiling point. So which one has the highest boiling point? Instinctively, we know that carbon and hydrogens are pretty bad at boiling, right? So they're going to have a very low boiling point. They're pretty basic, right? You're not going to go far being basic as a person. So just C and H, pretty bad. Like a sub question, what's the grouping for carbon? Is it a primary, secondary, or tertiary? Well, it's a secondary because that carbon is attached to 1 and 2 other carbons. 1, 2. So that becomes a secondary carbon. So that's 3 being the lowest. And what about this one? Well, is this one higher than that one? No. Turns out that we have H bonding right here, and H bonding occurs whenever this normal bonding isn't H enough, right? When it's not H enough, when normal bonding isn't enough, you get it, right? Haha, I know. So we are actually attached to a oxygen, so that occurs with H bonding, and H bonding is very strong bonding. It's very good. it takes a lot of energy just to break it down, just to boil it, right? So if you want to boil alcohols, it's going to take a lot of energy to break it. So this is going to be number 1, and by process of elimination, this is 2. This one experiences dipole moments right here. It's making it polar, and polar molecules tend to have good boiling point levels, but they're not as good as H bonding. So that's one to remember, right? So H bonding is like the best, polar bonding is okay, and then just normal carbon and hydrogen, it's terrible. It's absolute terrible. Now we're gonna kind of alter the question. Which one has the best water solubility? So number 1 has the best one, number 2 is okay, number 3 is like the worst, right? So which one is the worst? Well, I know that if you were to spill a bottle of oil onto water, it's not going to mix, right? Because the oil has a bunch of carbon and hydrogens, and it's nonpolar, and it's just branching, right? So whenever you have a molecule that only has carbons and hydrogens, it's very fatty, and fatty does not mix well with water. It's not miscible. So this one only has carbon and hydrogens, meaning that it would be number 3. It would be pretty bad. But what about this one and this one? Okay, well, they both have H bonding, so what do? Well, you could count the carbons. That's 1, 2, 3, 4, 5. Okay, so that's pretty good. 1, 2, 3, 4, 5, 6, and 7. There are more carbons attached to this alcohol than there are over here. Now, 1 through 6, or 1 through 5 carbons, you could say that it is soluble, and then 6 through whatever, right, is not soluble. Whoa. So you could say that whenever you have 6 carbons, you are sick. So 6 is sick, and whenever you're sick, you don't want to have sick water, right? You're not gonna count that as soluble. So 1 through 5 is okay, but 6, you're sick, and that's bad. So the more carbons you have, the less solubility you're gonna have. So this one would be 2. Still pretty good because of its alcohol, because of its H bonding properties, but it's not as good as this one, which is small and has great H bonding properties to it. Out of these 2 molecules, which one is going to have the preferred resonance hybrid? Which one contributes more to the hybrid, right? So it's more of a conceptual problem. There's no work involved, just concepts. We're going to separate these into 2 problems. So for problem 1, there's 2. Which one is going to be the preferred hybrid? Well, whenever you're looking at this, here's a set of priorities. So you go down the list. Priorities. Straight up, bonds, right? In big capital letters, bonds. And then after that, electronegativity. Okay, so which one has more bonds? That's what your brain should instinctively think. Well, let's see. 1, 2, 3, right? Okay, 1, 2, and 3. Well, that's okay. But what about this? 1, 2, 3, and 4. 4 of them. Well, you could say 4 and then 5. But still, that's a lot of bonds, right? Because oxygen has this carbon attached to carbon. Anyways, this one has more bonds, right? That has more bonds, and therefore this would be the priority group. It would be that one, since we have more bonds. It doesn't matter that oxygen is positive. Typically, we want oxygen to be negative, but in the case of resonance structures, the one that has more bonds is more stable. It's harder to break something that has more limbs than it is to break something that has less limbs, right? So you could take 10 sticks and try to break them, it's really hard. But if you only have 2 sticks and you try to break it, it would be kind of easy. Or you could imagine it with pencils. Alright, now we're going to do problem 2. So which one would contribute most to the resonance structure? Alright, well, let's count the bonds. That's the first thing you should think of. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Alright, well, bonds are equal, so we can't do that. Now we go to electronegativity. I would actually pick this one because oxygen is more electronegative than a neutral oxygen. The thing is, negativity goes from left to right. So the more right you go towards the periodic table, right, towards fluorine, that's going to be the most electronegative. So En, right? So oxygen really wants to be negative. It doesn't want to be neutral or positive, right? It wants to be negative. So compared to this neutral oxygen, a negative oxygen looks pretty good and would actually contribute the most to the resonance structure. For these 2 problems, I want you to identify the functional groups. Alright? Well, this is a pretty easy one right there. That's an alkene. That's an alkene, which is a double bond, king and queen. King and queen. Right? Alkyne would be a triple bond, which is 1, 2, and 3. 3 of a kind. 3 of a kind. Alkyne, right? Okay, well, this right here would be a what? An ester, because, well, you have your pavement right here, you have a sidewalk, you have your Easter eggs, everyone's finding Easter eggs, the babies are happy, it's Sunday, it's good. So you have Easter eggs with ester, so this would be an ester. What about this one? Well, you would think, oh, we're connected to an oxygen, yay, amide. Well, actually, it's an amine. This is an amine because amides have an oxygen with a carbon. That carbon is attached to a nitrogen. Do you see a nitrogen right here? We have an oxygen connected to a nitrogen. Is that the same? No, you're missing your double bond, you're missing a carbon. So therefore, since you don't have that, it's not an amide, it's going to be an amine. So we're still alone, kind of. It's just an amine. Amides only are available when you're connected to a carbon, and that carbon is directly attached to an oxygen. The reason why this is not an amide is because, well, you're not connected to a carbon, and that carbon's not connected to an oxygen. You're directly attached to an oxygen. So that's great. Now, for this one, what is this? What is this one? Well, you have a carbon with another carbon that's double bonded to an oxygen with a carbon. So this whole portion right there becomes a ketone, because oxygen is all alone ketone. Poor guy. It's a ketone. This is nothing. This right here is a carbon with an oxygen with another carbon. And so we are lost in a sea of C's. We are lost in a sea of C's. So that must mean that we are stuck in the ether, right? That's ether. Ether is surrounded by a sea of C's, carbon, right? And this right here is not a ketone. It's actually connected to an hydrogen. So you have a carbon with a carbon, an oxygen, and an H. And also, if that's the end, this is an aldehyde. So if you're taking the MCAT, an aldehyde only shows up on the terminal points at the ends. It's never in the middle. Ketones, however, which are derivatives of aldehydes, right? You just replace this hydrogen with the carbon, you get a ketone. Ketones can show up in the middle of molecules, so you can have this long structure and then ketone. And this would be an aldehyde, so they only show up in the ends, right? They kill chains, so that would be an aldehyde, right? Since they're chain killers, well, no one wants to be out, right? The carbon family doesn't want to be outside. They want to be inside, hiding from the aldehydes, right? Because they're chain killers. They kill molecules when they're chained. So they stop the chains, right? That's pretty cool. Hide from the aldehydes. So it's just memorization. Just work on your functional groups and you'll be fine. For these 3 problems, I want you to identify if these structures are resonance structures. Alright. Well, for the most part, if you want a kind of devil-may-care approach that doesn't work all the time, but it works a lot of the times, then here's what you do. This positive charge can actually, it doesn't matter if it's positive or negative, it can move only 2 molecules or only 2 atoms, right? So it can move 2 neighbors. That's 1 neighbor, 1, 2. Notice that our molecule now has a positive charge right there. So that is a sign of resonance. Also note that whenever you do this, your double bond has to move right here to the spot nearest to the previous location of the charge. So it is right here. So it's the same thing, right? And that's pretty good, right? So again, pluses or minuses can move only up to 2 atoms. If we only stopped over here and we had positive right there, or I should say if we moved only 1 atom, that would not be a resonance structure. It finished halfway, and that's not good. It needs to move 2 atoms. So these are resonance structures. However, if you want to be more proper and more analytical, you can draw out the hydrogens, which takes up time, but it always works. So let's do it. We have 1, 2, 3. Carbon wants 4 bonds. So we have hydrogen 1, 2, 3, and 4. Okay, that's good. What about this carbon? 1, right? You have 1, 2, 3, and 4. Well, actually, you would have 3, right? So you have 3. And 1, 2, 3, and 4. So that's H2. This will also be H2. This is H2. And what about this positive sign? Well, positive sign means that we're not going to have our 4 bonds. We're actually going to have 3 bonds. So you have a carbon with hydrogens. So 2, 4, 6, 7, 8. 4 minus 2 is 2 and 2. Or actually, you don't have those electrons, sorry. So whenever you want to be positive, you only have 3 bonds. You don't have any electrons to give out. So 4 minus 0 is 4, and 4 minus 3 bonds is positive 3. So that's how you become a positive charge. That means we only have 1 more hydrogen to put on here. That's the H right there. All right. So we move on to this one right here. 1, 2, 3, 4. All right. Notice that it has 3 bonds. That's positive charge. 3 bonds. We have a carbon like this. That's good. We don't want 4 bonds because we're positive. So again, this didn't change and this didn't change. We didn't add any hydrogen bonds. We didn't subtract any hydrogen bonds. That still is CH3 right there for this one. This is a 1, 2, H2. This is H2, H2. And 1, 2, 3. That's an H. So literally notice that literally nothing happened. That's an H. That's the same thing here. Same thing. Right here. That. This. That. Nothing changed. Resonance only happens whenever you move electrons, not atoms. Alright? So we didn't move any atoms. We have the same structure, just different placements of electrons. That would be a resonance structure. So what about this one? Well, notice that we don't have any negatives or positives, so we're going to have to do like classic hydrogen method. So that becomes a H3. This is 1, 2, 3. That's H. 1, 2, 3. That's an H. 1, 2, and 3. That's an H right there. That's a H3. yeah, and H3. Okay. So resonance only occurs when we have the same amount of hydrogens on the other side. Oh, this is resonance, by the way. So let's see here. That's H3 as well. Okay. And let's see, 1, 2, 3, and 4. That's H2. So carbon with another carbon with another carbon. You need 2 more bonds for this middle carbon, H. And notice that this carbon differs from this other one. Right? We only have 1 hydrogen, and then somehow we have another hydrogen. So somehow this hydrogen came out of nowhere, out of left field. That is not possible for resonance structures. You added an atom. You're not adding electrons. You're not moving electrons. You added an electron. So we're not the same. That is not even resonance. That's really bad. So instinctively, whenever you see that, there's no way, not a chance, that it's resonance. So you can automatically stop the problem. It's not resonance. Move on, okay? The hydrogen method takes a lot of time, but it works, right? It works. Sometimes you're gonna have to do the hydrogen method whenever you gotta just be double check, right? So if you wanted to do the plus method, it's not gonna work here. 1, 2. Okay, well, we don't have a positive right there. What about 1, 2? Well, we need it to be right here, so that's not possible. And you're like, man, well, I have to double check. Okay, well, it's not bad. We have 1, 2, 3 bonds on carbon, so that's an H to make 4 bonds. 1, 2, 3, 4, okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. All right, let's go to the other one. 1, 2, 3, 4. 1, 2, 3, and 4. 1, 2, 3, and 4. That only has 3 bonds to it, so let's do it right here because it's positive. So 1, 2, 3. So just 1 hydrogen. 1, 2, 3, and 4. 1, 2, 3, and 4 again. So we have H that matches with this H. We have an H that matches with this H. We have an H that matches with this H. And these two match with these two. So we have the same molecule, right? Just different placement of electrons. We didn't move, we didn't add, we didn't subtract any electrons, all right? So that would be a resonance structure right there. Resonance structure. So to recap, sometimes a speedy method is one where you can move the plus charge or negative charge to 2 neighbors down or 2 neighbors up, right? And that saves a lot of time, but sometimes it doesn't work, as you saw in this problem. Sometimes you're gonna have to do the hydrogen method. The way I was counting was like this. So here's how you count your hydrogens. Well, how many bonds does this carbon right here have, right? How many bonds do we have? So we have 1, 2, 3, right? That goes there, that goes here, that goes there. So 3 bonds. We want 4 bonds, so we're gonna make a hydrogen, right? What about this one? Well, that's 1 and 2. We want 4 bonds for hydrogen, so we're gonna have H2. Because that carbon is going to be like this. Making it 4 bonds, right? That's what you see. Right? And let's see, 1, 2, 3, 4. Okay? So just learn to count your carbons, count how many hydrogens there would be. Make sure to practice on your polarity, your hydrogen bonding, your solubility, your functional groups. That's really all there is. Your arrow pushing, it just comes down to practice. If you need more help, I recommend just going online and finding practice exams to work on, or practice quizzes, go on the internet, look at videos, or you can watch my video, which is like an hour long, okay? And just rewatch it on double speed. You can use it as much as you want. It's just here as a resource, all right? So I hope that these practice problems really helped you out. I hope that you do amazing on your exam. I know that you can do it because I gave you everything you need, and all you need to do is just believe in yourself. All right, have a great day.